Well, we've already talked about one final exam, but as a hobbit taking differential equations would say, sure, we've had one final, but what about second final? We're in luck. We have such a thing, the makeup final exam. And this gives us one more chance to have a little bit of fun as we do our differential equations. And the problems, some are very similar, but some are different. And so it's going to be fun. So let's just quickly go our last hurrah, and we'll do some more problems. Let's begin. Our first problem. Solve the ODE problem. X plus 1 y prime is equal to e to the negative y. And y of 0 equals 0. All right, so what kind of problem is this? Well, this is a classic separable differential equation. In other words, we can move the x's to one side and the y's to another side. So if we think about this, this is the same as x plus 1. Y prime we'll write as dy over dx is equal to e to the minus y. All right, now again, our goal, move the terms around so that all of the y's are on one side, all the x's are on another side. All right, so if we move this e to the minus y across, it'll become e to the positive y. dy equals 1 over x plus 1 dx. All right, so that's it. Notice we were successfully able to separate the variables. I mean, that's the key when we're talking about separable differential equations. Well, after you've done your separate, the next thing is to integrate. So we'll integrate both sides, and neither side is particularly bad. Integral of e to the y is e to the y. Integral of 1 over x plus 1, natural log of x plus 1. And of course, plus c. We only need one plus c. We don't need to put a plus c on both sides, because remember, constants can be combined together. Constants are like sponges. They like to absorb other constants. Now, we need to do two things. We need to solve for c, and because it says solve, we really should get y by itself. Now, we can do it in either order. Get y by itself, then solve for c, or solve for c and then get y by itself. Let's solve for c now. No reason that we can't. If we do that, what do we get? Well, notice this says when x equals 0, y equals 0. That's what this is telling us. So e to the 0 is equal to natural log 0 plus 1 plus c. Well, e to the 0, also known as 1. Log of 1, also known as 0, plus c. So we see that c equals 1. Great. So we're almost there. We have e to the y is equal to natural log x plus 1 plus 1. And the last thing is take the natural log of both sides. That brings the y down. So y is equal to natural log of x plus 1 plus 1. And there we go. Log. Yes, it's a log type of problem. And there are mathematicians who work with expressions which do involve things with log of log. You have many logs actually, because mathematicians, they really get into it. But there we go. Number 1. That's not so bad. See, these problems are going to be fun. All right. Number 2, an essay problem. Well, not that we have to write an essay, but it looks like we're going to have to read a little bit here. So, a tank contains 40 liters of fluid, which initially contains 5 liters of compound A and 10 liters of compound B. So there's some different chemicals floating around in this tank. We don't have all the chemicals, but we know 2 of them, A and B. Now, at time t equals 0, you know what? Before we go going too far, let's draw ourselves a picture, right? We see it's a tank problem, so let's just help ourselves. Okay, so we have a tank. We don't have to draw a great picture of a tank. It doesn't have to be realistic. But here we go. Here's our tank. All right, so we have our tank, and so we know initially, all right, it's 40 liters, and initially, what do we have? make some little notes here. There's 40 liters. There, A is equal to 5. There's 5 liters of compound A, and B is equal to 10. All right, so that's some initial information. So we really could have said, what does this mean? Well, what we're going to see is we have things which are going to vary. And so really we should say, oh, A, the amount at time 0 is equal to 5, and B at time 0 is equal to 10. All right, now let's keep going. At our time, t equals 0, a valve opens up. And it's going to continuously pump in 4 liters of fluid. Okay, good. So now we have things coming in. All right, so we have fluid coming into our tank, and it's coming in at 4 liters. And, okay, that doesn't say 4 liters per minute. All right, but whatever. We can think about whatever time units we want. But their total is 4 liters. But notice 2 of those liters are compound A, and 1 liter is compound B. So 2 of A and 1 of B. All right, good. Now, at the same time, a second valve opens up that continuously pumps out 4 liters. So here we see here's our 4 liters coming out. And everything's been well mixed. So how much of A pumps out? Well, it depends on how much of A is in the tank. It's the proportional amount of A that gets pumped out. Now, the question. Determine the time t at which the amount of compound A in the tank equals the amount of compound B in the tank. All right. Well, what's happening? Well, initially, what we see is that there's less of A and more of B, because that's what this says. A only has 5, B has 10. So initially, there's A is a smaller amount. Now, what happens? Well, what happens is we're putting this fluid into the tank, and if you look at it, there's more of A than there is of B. And if you think about what happens whenever you're pumping into a tank, what's going to happen to the liquid that's in the tank is that it's going to look like what you're pumping in. Because in the long run, it's all going to mix in and resemble, as time goes into infinity, what comes in. So in the long run, there's going to be more of A than of B. So we start with A below B. In the long run, we end with A above B. So there has to be a time when they cross. So there has to be a time when A and B are the same. All right. So that's our goal. What's the time when they're the same? So how do we figure this out? Well, what we can do is we can say, well, let's think about there as not being one big mixing problem, but really there's 2 mixing problems. What's happening with A as it's being mixed and what's happening with B as it's being mixed. And then we'll put the 2 together and get what we need. Okay, so let's start with A. So mixing of A. Now, what can we say? Well, what we'll do is we'll say, how is A changing? Now, we see that A is changing in a particular way. At every moment of time, we have 2 liters coming in. So the inflow is 2. So this is our in. Now the outflow, well, we have 4 liters out of 40. Notice that the amount coming in and amount going out is equal, which means that there's always going to be 40 liters in the tank. So since 4 liters pump out, there's a total of 40 liters. That means 1/10 always gets pumped out. Since it's well mixed, that tells us that 1/10 of A is going to be pumped out. So in other words, 1/10, that's the proportion that gets pumped out. So how much of A gets pumped out? 1/10 times however much there is of A. So that's our out. And we have our initial condition, namely that a of 0 equals 5. That comes from here. All right, well, now we solve. And this is actually a pretty straightforward one. So a prime plus 1/10 times a is equal to 2. And our integrating factor, e to the integral of 1/10. So we have e to the integral of 1/10 t. So if we use our integrating factor is e to the 1/10 t, what we'll have is that the left-hand side, that's really the derivative of a times e to the 1/10 t. It's always a function times your integrating factor. Well, that's equal to 2 e to the 1/10 t. And now we integrate. And we say, okay, a e to the 1/10 t is equal to, well, here we're going to have 2 divide by 1/10. Well, if you take 2 divide by 1/10, what would that be? Well, be the same as multiplying by 10. So that'd be 20 e to the 1/10 t, and plus a constant c. So now, how do we find our constant? We'll plug in 0. And we get a of 0, which is 5, e to 0 is 1, equals 20, e to the 0, again, is 1, and plus c. So that says, aha, c has to be 15. Well, actually, excuse me, negative 15, right? Because 20 minus 15 equals 5. And finally move that e to the 1/10 t across, and we come to our conclusion. Lo and behold, a is equal to 20 minus 15 e to the 1/10 t. Now we can see if this, negative, because I'm dividing by 1/10, so that's negative in the exponent. Now the question is, does this match our expectations? Well, we see it matches at time 0. As we let t go into infinity, what happens? Well, as t goes to infinity, this is e to a large negative number, which means this last part goes away, so it goes to 20, which means half of the tank will be compound A. Does that match our expectations? The answer is yes, because remember we talked about this just a moment ago. You see how half of what's coming in is compound A. So half in the future is what we should expect. What is in the tank should match what's coming in. So yeah, good. That's good. That matches our expectations. Now, that's our first mixing problem. See, the fun continues because we have a second mixing problem, which is we're going to talk about the mixing of our compound B. Now, very similar. What happens? Well, it's still, how does B change? Well, there's 1 coming in, and then we're going to subtract 1/10 of what's currently in the tank. Same idea, because we have 1/10 of everything comes out, so 1/10 of B comes out. So we have our in, subtract our out, and the process is going to be like, wow, deja vu. Yeah, it's really the same setup. The only thing that changes, 2 things, is that this 1 versus this 2, and that comes from our what's coming in. The other thing is our initial conditions. So here, at time 0, we have 10. Previously we had 5. But other than that, the process is the same. So in particular, we still have the derivative of b e to the 1/10 t is equal to e to the 1/10 t. Integrate both sides. Got a little bit ahead of myself. b e to the 1/10 t is equal to, and then here, divide by 1/10, same as multiply by 10. 10 e to the 1/10 t plus a constant. And what do we do? Well, we plug in at time 0, we're 10. So we get that 10, e to the 0 is 1, is equal to 10 plus d. All right, well, what does that tell us? That tells us, aha, d equals 0. That's okay. And so now, if d equals 0, we divide e to the 1/10th t, and we come to the conclusion that b is 10, which means b doesn't actually change. Now you might say, in retrospect, this is obvious, right? Because what we see is that we already have 1/4 of the fluid is b, and 1/4 of what's coming in is b. So yeah, we'll always have 1/4 of it will be b. Yeah, well, that's one of those things in retrospect that may be obvious, but was it? Now that we've done the work, we're like, yeah, okay, we can see how that's true. All right, so we've done our two mixing problems, and the question is, when do they match? So we need to set these two equal to each other. So the question is, when does 10, that's our b, equal to 20 minus 15 e to the minus 1/10 t? Whoops, 1/10. There's a 10th there. Bad handwriting. All right, we'll move things around, and what do we see? Well, okay, move the 10 across, move that minus 15 across. We need to have 15 e to the minus 1/10 times t has to equal to 10. All right, divide both sides by 15, and there's a common factor of 5. So you get e to the minus 1/10 of t has to be equal to 2/3. So minus 1/10 t is log of 2/3, which, by the way, is the same as minus log of 3/2. In case you notice, I want to get rid of the minus signs. And finally, multiply through both sides by minus 10. And we're just out of, there's a little space down here in this corner. And so we can say our answer is, this will happen at time is equal to 10 natural log of 3/2. That's it. That's the answer. 10 natural log 3/2. What a good answer. That was a fun problem. And it's kind of one of those things that's like, are we able to do this? Because there's like two things going on, and it's not a systems problem. Because it's not that A is affecting B. It's just that we have something going on with A and something going on with B, and we just need to solve them individually and then compare the answers. Good times. Good times. I like this one. Well, I like all problems. It's a bias of mine. But it's hopefully not a bad bias. All right, number 3. A horizontal spring mass system has the following details. There's the mass, there has 2 kilograms, and there's a spring constant, which is 18 Newton meters. Or newtons per meter, I guess, is how you read it. Now, in addition, there is an external force of 4 sine t acting on the mass. Now, nothing is said about damping. So, what do we assume? Well, if there's nothing said about damping, we assume no damping. All right, great. No damping. That makes it easy. Now, all right, so suppose that the mass is displaced to the left, negative, from its equilibrium by 1 meter, and then released from rest at time t equals 0. Set up an initial value problem and solve to find the position x of t for t in seconds. Now, setting it up, that's not too bad, because what do we have? We know it's a spring mass system, so we have our basic formula. We have something x double prime plus something x prime plus something x equals something, right? That's our generic form for spring mass, where these are constants, and this can be interesting. Now, what are the constants? Well, what goes in front of the x double prime is the spring constant. So that's, not the spring constant, that's the mass, mass. The spring constant goes in front of the x. The x prime is the damping. There is no damping. And this box is the external force. So that's 4 sine of t. All right, so that's our differential equation. But remember, it says set up an initial value problem, which means we also need to specify our initial conditions. So we need to know what's x at time 0 and what's x prime at time 0. Now we're told it's moved to the left and it's also negative. So initially, that says our position is at -1. And then it's released from rest. What does it mean to be at rest? It means we're not moving. So if we're not moving, that says x prime is 0 is equal to 0. So those are our initial conditions, and we'll rewrite this a little bit cleaner. 2x double prime plus 18x equals 4 sine t. So that's part of our answer. Now, of course, we could divide through by 2, and we'll do that in just a second. But in terms of the setup, that's what we need to do. But the problem's not done, because there's this and solve. So we also need to do some solving. That's all right. We're solving machines. We can do it. We can do it. So how do we proceed? Well, this is not too bad. So notice it's x double prime plus 18x equals 2 sine of t. And what do we see? Well, constant coefficients. So that's good. We like those. And it's non-homogeneous, which means there's something on that other side. Now the constant coefficients, that's not too bad. It means we can solve. The non-homogeneous says, oh, we got to handle that 2 sine t. And there's a couple ways to do that. There's variation of parameters, and there's a method of undetermined coefficients. But sine of t is just such a beautiful expression. Method of undetermined coefficients is right up our alley. So the way we'll proceed is we'll start by solving the homogeneous part. So we'll have x double prime plus 18x, set it equal to 0. Turn this into polynomial problem. Whoops, why did I say 18 here? I forgot to divide the 18 by 2. That's 9. I was looking like that. That doesn't look like a nice number. So r squared plus 9 equals 0. Says our roots are plus or minus 3i. Okay, that's not bad. Complex roots, pure complex roots. Not even, a little bit of real part. There's no real part. That says our solutions have the form something cosine 3t plus something sine of 3t. All right, so that's the homogeneous part. And now we say, okay, does sine t, does that look like anything there? And the answer is no. And you might say, well, it kind of looks like sine of 3t. Yeah, but not sine of 3t. That 3 is important. So that says, okay, good. So we could call this, sometimes we call this xc, the complementary solution. And all right, well now we have to turn to the particular solution. So let's put our energy to there. So, well, it's some constant sine of t, because we need to end up with sine of t over there. And whenever there's a sine cosines come in pairs. So there's also a possibility that there's something of the form some constant times cosine. So that's what our particular solution looks like. There's nothing else that will show up. We don't need to worry about adding factors of t because there's no overlap. We don't have to worry about any other functions because no other functions show up. Only the possibilities are sine and cosine. Now the nice thing is it's pretty easy to take the second derivative of this. First derivative, well, is c cosine t minus d sine t. And second derivative, minus c sine t. And then we're going to have a minus d cosine t. All right, so now we have our first, second function, and we plug it in to this expression. So what do we need? Well, what we need is we need x double prime plus 9x equals 2 sine t. All right, so we're going to say, okay, x double prime minus c sine t minus d cosine t. So there's our x double prime plus 9 times our c sine t plus d cosine t. All that, and we ran out of room, but all that equals 2 sine t. All right, well, okay, that's not so bad. We can put things together. We have minus c, here's plus 9c, so that means 8 times c sine t. And then we have plus 9d, subtract d, plus 8 times d cosine t equals 2 sine of t. Well, what does that tell us? Well, it tells us a lot, actually. Notice there's no cosine t over here, so that says that this part needs to go away. All right, well, the only way that can happen is if d equals 0. Now, the sine t's have to match, so that says that the 8c has to equal 2. Okay, so that tells us c has to equal 2 over 8, which is 1/4. And so we have, the conclusion is that our particular solution is 1/4 times sine of t. Okay. Now, we have our complementary solution, we have our particular solution, and our next step is to put them together, because we're still not done yet. We have to find our total solution, and to do that, we really need to use our initial conditions. So, what do we do next? Well, we have our function x looks like 1/4 sine of t, our particular solution, plus some to be determined constant, cosine 3t, plus some other to be determined constant, sine of 3t. And we're going to use information about x of 0 and x prime of 0. So let's also write down what is x prime. That's 1/4 cosine t, then minus 3a sine of 3t, and plus 3b cosine 3t. So we plug in 0. When we plug in x of 0, what do we get? Well, we're going to get 0 and a and 0. So we'll get -1 has to equal a. That's pretty good. We can solve for a. Yeah, we can really solve for a. Now, x prime is 0. Well, we're going to get 1, remember that's 0. We're going to get 1/4, and then we're going to get 0, because that goes away, and then we're going to get 3b. Okay, so 1/4 plus 3b. All right, great. So we can solve for this, right? What do we do? Well, we subtract a fourth across and divide by 3. And if we do that, we say, b has to be minus 1/12. Now we have everything. We have everything we need. So our final answer is we plug in a, plug in b, and we get the following. So x is equal to 1/4 sine of t. A is -1, so minus cosine 3t, and b is minus 1/12 sine of 3t. And we're done. We're done. That's it. Yay! Woohoo! Good job, us! All right. Well, that wasn't so bad. There's definitely a process here. And, we had to know how to set up spring mass. We had to know how to handle constant coefficient non-homogeneous, which means we did the homogeneous part. We did the particular solution. We put it all together. We solved for initial conditions. Actually, that sounds like a lot. But we're good. We can do it. We can do it. All right. Well, on to our next problem. Number 4. Find the solutions x of t and y of t of the system of differential equations x prime equals x minus 2y, y prime equals 2x plus y, with initial conditions x of 0 equals 1 and y of 0 equals negative 1. All right, well, let's figure it out. Now, we see systems, and it doesn't tell us we have to use our eigenvalue methods, our matrices methods. We don't have to, but we put a lot of work into learning that, so let's do that. So if we think about this in terms of matrices, what we really have is we'll think of it as we have our system x prime, and you can't tell by my handwriting, but I've written this in a bold x. So this is a vector. So in other words, I'm going to think of our bold x as being the vector of xy. So x prime, that's this part here. That's equal to, gather the coefficients, 1 minus 2 to 1. Now, if they were being mean, they might do something like x minus 2y, y plus 2x. And like, oh, no, make sure, the coefficients are all in the right places, right? So it's xy, xy, yeah. No worries, no worries. We got this. Okay. And our initial condition for our vector is that x of 0 is 1 minus 1. Okay, so that's what we're after. Well, we begin. So eigenvalue method says first find the eigenvalues. All right, so we're going to take our determinant of a minus lambda I. So that's determinant 1 minus lambda minus 2 to 1 minus lambda, which is 1 minus lambda quantity squared, subtract 2 times negative 2, which is really adding 4. And, okay. And, all right. So, what does this become? Well, we can actually save ourselves a little bit of work here. Set it equal to 0, right? And we see a square plus a square equals 0. Oh, that sounds a little bit complex, right? Because I can't have a positive and a positive end up with 0. That's not possible. Well, you can if complex numbers are involved. Notice we can be a little bit, right? Because this is 4, so that says, hey, 1 minus lambda squared, which by the way is the same as lambda minus 1 squared, has to equal to negative 4. These two are the same. So 1 minus lambda quantity squared, lambda minus 1 squared. This plus 4 comes across as minus 4. Or we say, that says lambda minus 1, taking the square root of both sides, plus minus 2i. We need the I because of the minus. So our eigenvalues are 1 plus or minus 2i. Complex. All right, that's okay. We know how to handle complex eigenvalues. Now, we need the eigenvectors. Well, we only need one eigenvector. So let's suppose that we're going to focus on lambda equals 1 plus 2i. All right, so I'm going to plug it into a minus lambda I. And let's see what we have. Well, that's going to be 1 minus 1 plus 2i, so that makes it minus 2i minus 2. And then we're going to have 2 and minus 2i. All right, so that's our a minus lambda I. And now what we're looking for is we're looking for some vector. So if I multiply this by ab, I get 0, 0. Right? That's how we find our eigenvectors. Well, we know that there's going to be redundancy because there's really two equations here. There's the minus 2i times a minus 2b equals 0, and there's the 2a minus 2i times b equals 0. So let's suppose Well, just to help, I'm going to write these down again. So our first equation, minus 2i times a minus 2b equals 0, and 2a minus 2b times I equals 0. Now, they're redundant, which is to say, if I look at these equations, they're the same. I'm not getting any new information. So I can cross one out, doesn't matter which one. And this one, well, I can cancel the 2. And this says, look, A has to look like B times I. So our vector, what we have is that AB looks like, since A equals BI, looks like B times I times B, or if you like, that's BI1, or, this is the nice thing, B, anything that says 0, 1 plus I1, 0. All right, now that's going to be important in just a moment here. All right, so now we have our eigenvector associated with this eigenvalue. And what we can do is we can get a solution. And the way we find our solution is we say a solution would look like what? Well, it would look like e to the lambda I times t, so e to the 1 plus 2i times t times our eigenvector, and this is our eigenvector I1. Okay, but we can get both our solutions and get rid of complex numbers if we do a little bit more work. And how do we do it? Well, okay, the first thing is we rewrite this expression. So what is it? Well, the first part, that's really e to the t cosine 2t plus I e to the t sine of 2t. Now, the e to the t's is because the real part is 1. The cosine 2t sine 2t is because the imaginary part is 2. So that's where those 1s and 2s come from. And this is de Moivre's formula on the first part. Now, the second part, we do what we did down here. This is the vector 0, 1 plus I times the vector 1, 0. And now we need to do a little bit of distribution. Okay, which means we're going to do the following. We're going to take the real parts and the imaginary parts, whoops, sorry about that, and multiply them together and see what we get. So what we get, we'll get 0 e to the t cosine 2t, and then 1 times e to the 2t cosine 2t. So I can write that as e to the t cosine 2t. So I'm making a vector here. I'm going to multiply these together and add these together. Here, because I get 0 and then 1 copy downstairs. Now, on the other hand, when I multiply the imaginary parts together, well, the I squared means we're going to subtract, and then we have the upstairs is a 1, so we get minus e to the t sine of 2t, and then the downstairs, we're going to get 0. So there is a first solution. All right, so we'll put times a constant a. All right, not to be confused with the matrix A, this is a constant a. I know, it can be confusing. Next thing is we're going to do the real part of the first, the imaginary part of the second. Okay, so it's e to the 2t cosine 2t times that vector. Well, that'll give us an e to the t cosine 2t upstairs and 0 down. All right, and then we're going to take the imaginary part there times the real part there. And here we get 0 upstairs, and downstairs we'll get e to the t sine of 2t. And well, there'll be a b. So this is the general solution to that problem. X prime equals this vector, this matrix 1 minus 2, 2, 1x. All solutions have this form. What we need to do now is find a and b. And the good news is it's going to be pretty straightforward. So how do we do it? Well, what we do is we plug in 0. And we say, okay, so we're going to get a, and when we plug in 0, we're going to get the sine part goes away, and the cosine part is going to become 1. So a times 0, 1, plus b, and here it'll be 1, 0, has to equal, well, if you add it up, you get b, because you get 0 plus b, and a equals 1 minus 1. So we see, aha, lo and behold, we know what a and b are. So we see that a is really minus 1 and b is really plus 1. All right. Now, are we done? Well, almost. There's one small detail. Technically speaking, if this was our problem, this is our answer. And we're correct. That works. But that wasn't our problem. We modified it, right? There was a step when we went from here to there. So now we need to unwrap. And what does this unwrapping mean? Well, what do we need to do? We need to find functions x of t and y of t. So we're not looking for some vector valued expression. We're looking for x and y. Well, what are x and y? Well, x is the top entry and y is the bottom entry. So the last thing is to extract the top and the bottom. So we can do that. Give ourselves a little bit of space here. So we see that x, we read off the top entry, minus minus makes e to the t sine of 2t, and then plus e to the t cosine 2t. Okay, right? Minus minus plus 1 times, all right? And y, well, minus e to the t cosine of 2t, and then plus e to the t sine of 2t. And we're done. That's it. That's the answer. Right there. See, we had just enough space. We got it in. Good for us. Good for us. It's nice when a plan comes together. All right, so that's number 4. Halfway. Woohoo! Halfway there. Halfway there. Or we should be chanting, have to go. Have to go. Number 5. For the system of differential equations, a system problem, x prime equals ax, a is 1, 1 minus 4, 5, x of 0 equals 1 minus 2. First, find the matrix exponential, e to the at, and then use it to find the particular solution, x of t. All right, so here we go. And, well, what do we do? First, find the eigenvalues of a. That's always the first step. Because when you're looking for e to the at, there's a couple of ways to do it. If we're lucky, it's a 2 by 2 with repeated roots. Because then it's like, pow, there's a really fast way to do it. But even if we're not lucky, once we have the roots, we find the solutions to the differential equation, and then we make the fundamental matrix, and once we have the fundamental matrix, we modify that and get e to the at. Well, let's find out which one we have. Okay, so we have, well, again, determinant a minus lambda I. So we're looking at the determinant 1 minus lambda 1 minus 4 and 5 minus lambda. Okay, so that would be 1 minus lambda times 5 minus lambda, subtract negative 4 times 1. All right, what would that be? Well, in the first part, you'd have lambda squared. Then we'd have a minus 5 lambda and a minus lambda, which would make this minus 6 lambda. Then we'd have 5 plus 4, which makes it plus 9. Or, oh, that's actually kind of nice. It's almost like they planned it to be nice. Because they did. And that is lambda minus 3 squared, which means our eigenvalues are repeated roots. So we have 3 and 3. Now, why do we like that? When we have repeated roots for 2 by 2, it's really slick to find the matrix exponential. So here's the generic formula. So in general, if your eigenvalues are lambda lambda, then e to the at is equal to e to the lambda t times, you take the identity matrix, which is the matrix 1, 0, 0, 1, and then you add to that your a minus lambda I times t. And that's it. That's it. That's the whole expression. Okay, so in our case, we would have e to the 3t, identity matrix 1, 0, 0, 1. And now a minus, here it's 3i. So basically we're taking this matrix and plugging in lambda equals 3. So it's minus 2, 1, minus 4, 2 times t. So if you multiply this out, well, this is e to the 3t. Then we have 1 minus 2t, t, right? Minus 4t, and 1 plus 2t. And that's it. That's the answer. And we're done. We're done. Well, not quite. So this is our e to the at. Okay, so that's good news for us. So that is part of our answer. But to finish it up, to do the whole problem, the other thing that we need to do is that we need to solve for the particular solution, right? Use it to find the particular solution. Now for that, well, once you have e to the at, it's really quick, because that's why we want e to the at. It makes this next step very fast, very efficient. And what happens is you take e to the at times x0. So for us, that's e to the 3t. We have our 1 minus 2t, t, minus 4t, 1 plus 2t, times 1 minus 2. So that becomes e to the 3t, 1 minus 2t times 1, and then subtract 2t. So that'd be 1 minus 2t, and we'll go ahead and plus minus 2. We'll do it slowly here. And then the next part is 1 times minus 4t, so minus 4t. And then minus 2 times 1 plus 2t, so plus minus 2 minus 4t. Which leaves us with e to the 3t, and then it'll be 1 minus 2t minus 2t, 1 minus 4t, and then we have minus 4t minus 4t, that's minus 8t, and then there's a minus 2. So minus 2 minus 8t. And that's the answer. There we go. Ah, wow. Whew. What a problem, right? Well, actually, that doesn't seem too bad at all, if you knew it. Now, you might say, could we have done it a different way? And the answer is yes. Will you show us that way? I'll let you work it out. But now that you know the answer, if you don't end up with this, troubles. All right, so that's number 5. Now, what does that mean? It means we're up to number 6, which means we better have our Laplace transform table ready to go, because that's the next thing. All right, here we go. 6. All right, find the Laplace transform of cosine 3 tau times t minus tau e to the t minus tau d tau. All right, and write your answer in a nice polynomial form. Okay, so what's happening here? So we're going to do part A before we do part B. So what do you have? Well, if you think about this, what does this look like? You might say, as you look at the table, And let's just stare at the table for a second. You might say, wait a second, there's not an integral anywhere to be seen. Or is there? Well, there is actually a nice little fact. It's this fact right here. F star G. That's convolution. And what do we need? Well, we need to know what F star G represents. So F star G of t is the integral 0 to t of f of tau g t minus tau d tau. And if you look, that's what we have. Okay, great. So we see this is a convolution. And so what do we need? Well, we need to know what is our f, what's our g. And once we know that, we say, oh, then you individually take the Laplace transforms of those. And once you've done that, you multiply the answers. All right, so away we go. So what we're looking for is we're taking our convolution, and we're just trying to figure out what are our parts. So cosine 3 tau, and then we have our t minus tau e to the t minus tau. And we say, all right, great. Well, what's our f of tau? What's our g of t minus tau? And it's not so hard to see. So we think of this part right here. This is our f of tau. And in particular, we can think of f of t as the cosine of 3t. Here, this is our g of t minus tau. So our function g looks like t e to the t. All right, so now we have f, we have g. And we're going to put this together. So what happens? Well, we take each individual one. So the cosine, that's on our list. See, cosine 3t, s over s squared plus 9. All right, so write that down. So this would map to s over s squared plus 9. Now, on the other hand, t e to the t, that shows up here. So that would be a equals 1 over s minus 1 squared. So this goes to 1 over s minus 1 squared. And now convolution says we multiply the results together, so we times those together, and therefore our answer, well, s times 1 is s, and downstairs we have s squared plus 9 times s minus 1 squared. And that's it for part A. Aha! Not so bad. Not so bad if you know what you're looking for. If you don't, you're like, well, this is going to take a while, because it might take a while. It's not that it's impossible, but lots of paper would be involved. Part B. Find the inverse Laplace transform of this expression. 2s minus 5, e to the minus 2s, s minus 3, s minus 2. Now, basically every inverse Laplace transform more or less looks like this. You have some polynomial over polynomial times perhaps some exponential piece. Now, the exponential piece you should move to the side. So really we should think of this as 2s minus 5 over s minus 3, s minus 2 times e to the minus 2s. This part is signaling that our answer will involve a shift. That's all right. We'll deal with that when we have to. And then the first part is partial fractions. You should expect partial fractions. When you're doing Laplace transforms, that's the big thing. Partial fractions. Partial fractions. All right, so we're into part B. All right. So, all right, a over s minus 3 plus b over s minus 2. Clear out our denominators, which means multiply both sides here by this quantity. s minus 3 times s minus 2. And if we do that, we get 2s minus 5 is equal to a times s minus 2 plus b times s minus 3. Time to make some good choices. For example, preparing for the exam. A good choice. Now, what do we get? When we plug in 2, we see 4 minus 5, that's minus 1, equals 0. And then we have b times 2 minus 3, well, that's minus b. Okay, so b has to equal 1. If we plug in 3, we get 6 minus 5, which is plus 1, is equal to a times 3 minus 2, which is plus a, and b times 0. The good choices, of course, as a reminder, make zeros. Zeros are our friend. You know, as we wind down our math knowledge towards the end of our math courses, or even at the end of the semester, it's nice to remember 0 is a friend. We like 0. 0 is our good friend. All right. As long as it's not your score. That's not a friend. Well, that's a different story. All right. So what do we have? Well, what we have then is that our original expression really looks like 1 over s minus 3 plus 1 over s minus 2. And don't forget there was this e to the minus 2s. The e to the minus 2s is not involved in partial fractions. That's moved to the side, and we pull it back when we need it. Now, the good news is we know how to handle these pieces. And in particular, whenever we see 1 over s minus a, that looks like e to the at. So, if I saw 1 over s minus 3, we say, hey, that should be e to the 3t. 1 over s minus 2, that should be, e to the 2t. But there is this e to the minus as. So we need to make sure we account for that. And the way we account for it is this line right here. This is a really important line. And so what it's telling us is that we're going to be doing a shift. And shifting by how much? We're going to shift by 2. Okay, so this tells us shift by 2. And all right, so when we say shift by 2, our function shifts by 2, and there's an on-off switch at 2. So here we go. Our final answer, well, that's e to the 3t minus 2 plus e to the 2 times t minus 2. So that's our function shifted. So when we say shift, just replace t by t minus the shift. So t becomes t minus 2. Same thing happens here. And then multiplied by our unit step function times t minus 2. And that's our answer. We're done. We're done, right? And this will always be the flow for these types of problems. Whenever you see a find the inverse Laplace transform, like, okay, move the exponent to the side, do the partial fractions. All right, figure out what the individual pieces do, figure out what your shift is, and put it together, and life is good. And with practice, these things become automatic. And that's good. It's really good when it becomes automatic because that means you're succeeding. When things become automatic, that means you get to enjoy it. Like, this is fun. Look at how beautiful these numbers are. No weird fractions. Life is good. You're going to pass the class. All right. Number 7. Solve the following differential equation using Laplace transform. Aha! All right. Y double prime minus 2y prime equals a lot of stuff. Whoa. What? Huh? All right. Well, let's figure it out. So we have that unit step function, which means there's an on-off switch. And we're multiplying it by 4 cosine 2 times t minus 1 minus 4 sine 2 times t minus 1. Now, the nice thing is, you'll notice all these things match up. Now, that's good for us. We like that. Because if we go back to our table, that's the nice part. And it says, oh, in your answer, there's this e to the minus thing, and then there's this function involved. Okay, so let's start. Now, the way we solve a differential equation using Laplace transform is we take the Laplace transform of both sides. So we'd have the Laplace transform of y double prime minus 2 times the Laplace transform of y prime is equal to the Laplace transform of, I guess these should have been squiggly braces, right? Well, maybe. All right, and then there's this u, t minus 1, 4 cosine 2 t minus 1 minus 4 sine 2 t minus 1. Wow. All right. This might look a little bit, but perhaps things will get nice. I hope. I hope. We want things to be nice. And that's why we study math, right? We like nice things. Now, for the second derivative, there's a nice formula that we can refer to. So for the second derivative, it's s squared times the function we're after. Then don't forget there's a minus s times function at 0 and minus the derivative at 0. And I'm not going to refer back again here, but the x prime will also need s times function we're after minus the function at 0. All right, so we have, this will become s squared y of s and minus s times what's happening at 0, which is 2, minus the derivative at 0, which is 4. Then minus 2, our s times our function y of s, and subtract what's happening at 0, which is 2, is equal to, now we come to the other side. Now, this u t minus 1, everything is t minus 1. That's what we want. We're not like, oh man, everything has t minus 1. Like, whew, everything already has t minus 1. So, because of that, we know we're going to have an e to the minus s. So, right, because everything's in terms of t minus a, you have e to minus as. And then we say, okay, well, what happens here? So we're going to think of this as being the 4 cosine 2t. That would be the unshifted, and minus here 4 sine of 2t. Again, we're thinking of it as the unshifted parts. So what happens when we take these transforms? Well, we're going to have the 4 and cosine 2t. All right, back to our table. You might say, shouldn't we have this memorized? Yeah, someday. So s over s squared plus a squared. And for sine, it'd be a over s squared plus a squared. So just so we have that, so we would have s over s squared plus 4, and then minus 4. And here what we would have is we would have a, which is 2, over s squared plus 4. All right, good. Now, that's what we have currently. Time for us to get to work. So, what do? Well, we start chipping away. Let's put the y of s terms together. We have s squared minus 2s. So s squared minus 2s times y of s. We have minus 2s. Okay, so that's minus 2s. And then we have minus 4. And there we have plus 4, which cancels. So 0. All right, that's good news for us. On the other side, well, we can pull the 4 out. So we have 4 e to the minus s, and then times s minus 2 over s squared plus 4. All right. Good. That's not too bad. All right. Well, now what? Well, okay. As we start moving forward, we need to get y of s by itself. So we can move the 2s across. And so we'll do that first. S squared minus 2s. times y of s is equal to 2 times s plus 4 e to the minus s times s minus 2 over s squared plus 4. And I just want to point something out here. I just noticed. Notice here I have s, and there s minus 2. And if you look at s squared minus 2s, that's s times s minus 2. It's like, what? That's amazing. It's almost like they planned it to happen. Because they did. It was planned this way. Yes, this was all intentional. Because what's going to happen? Well, we're going to now divide, and we'll see that y of s is equal to what? Well, in the first place, when we divide by s times s minus 2, the s's cancel. So we're going to get 2 times 1 over s minus 2. And in the second case, the s minus 2's cancel. So we're going to get 4 e to the minus s times 1 over s times s squared plus 4. So that's actually pretty good for us. Now, the first term is good to go. No more work needs to be done, no partial fractions. That's great. The second one, we need to do work on. So partial fractions, but of course, we're so used to partial fractions when we're doing Laplace transforms, we'd almost be more surprised if there wasn't partial fractions involved. We'd say, what? No partial fractions? Is it my birthday and nobody told me? No, we got to do it. Come on. All right. So let's do our partial fractions. Give ourselves just a touch more room. And, okay, so 1 over s times s squared plus 4. All right, that looks like something over s plus, now this is irreducible quadratic, so we have to put a little bit more upstairs, a little bit more oomph, so that we can account for all possibilities. So bs plus c over s squared plus 4. Clear the denominator, so multiply both sides by s times s squared plus 4. And what do we get? We get 1 is equal to a times s squared plus 4, because the s's cancel. And then we get plus b times s plus c times s. Now from here you can solve for a, b, and c by plugging in numbers, or you can expand out and group by coefficients. So for instance, you could say, what do I have for s squared? Well, you have an a and a b. So this is a plus b times s squared. Okay, all right, that's fine. And then for s, there's just a c, so c times s. And then for a constant, there's just a 4a. And now we start saying, hey, you know, looking at these coefficients, we need to have the constant term has to match the constant term. So this equals 1. What's in front of s has to match what's in front of s. So that equals 0. What's in front of s squared has to match what's in front of s squared. So that equals 0. So we come to the conclusion, a equals 1/4, b equals, well, a plus b equals 0. So b is minus a minus 1/4, and c equals 0. Now, I feel silly. You might say, why? I forgot the 4. The 4 times force makes things a little bit cleaner. Okay, so updating. Now that we've done our partial fractions, we can say, okay, our new y of s is equal to 2 times 1 over s minus 2 plus, we have e to the minus s, and then there's this 4. I'm just going to multiply it through. So we have a over s. So a is 1/4. So a over s, 1/4 times 4 makes 1 over s. And then b times s plus c. Well, b is minus 1/4. So we have, okay, so it's minus 1/4 s times the 4. So I'm using this 4 here, which would make this a minus s over s squared plus 4. Remember that c is equal to 0. All right, and now we're ready to run our inverse Laplace transform. Everything's in our nice form. So, a couple of things. We've seen things that look like 1 over s minus 2. That would become e to the 2t. 1 over s, well, that's 1. It's a very nice one. S over s squared plus 4, well, we've seen that before. That's cosine. So that's our cosine 2t. All right, well, what's missing? The e to the minus s. Now this says what? Shift by 1. All right, now we have all our pieces, and we're ready to put it all together. So our final answer, we have 2 e to the 2t plus our shift by 1, so u t minus 1. And then we have 1. That's there. And then we're going to subtract cosine 2 t minus 1. And that's it. We're done with this problem, right? And because we figured it out, right? We have our 1. 1 shifted is still 1. We shifted our cosine function, and we remembered to turn on our switch. And so everything worked out. Everything worked out really nicely, almost as if it was meant to be, because, well, it was meant to be. All right, well, that brings us to number 8. All right, find the recurrence relation for the coefficients in a power series solution, y equals the sum n equals 0 to infinity cn x to the n. So that's what we mean by power series solution, something of that form, of y double prime plus 2xy prime minus 3x squared y equals 0. And it says if y of 0 equals 4, y prime of 0 equals 3, find the first 5 terms of the series. So we're going up through c fourth x to the 4th. All right. So here we go. Now, there's a lot of things which are mechanical. And what are the parts? Well, we say, look, we know what y looks like. It's the sum n equals 0 to infinity, cn x to the n. You might say, how do we know that? It's right there. Oh, you mean you copy? Yeah, we copy. Now y prime, well, we just take the derivative. And we take the derivative term by term. So there's, whoops, forgot to write. And n comes down, x to the n minus 1. And y double prime, our sum goes 0 to infinity, cn n minus 1, x to the n minus 2. All right. So next up is put things into here. So what do we have? Well, we get y double prime. Remember this is 0 here. I'll write that first. Y double prime plus 2x y prime minus 3x squared y becomes, well, y double prime, that's this piece here. So we have the sum 0 to infinity of cn times n minus 1 x to the n minus 2 plus 2x y prime. Sum n equals 0 to infinity cn times n x to the n minus 1. And then minus 3x squared times y. Sum 0 to infinity cn x to the n. All right, so now we have our pieces, and we are going to do the next thing. Again, this is not too bad. We're going to move stuff in. And Okay. So, if we do that, we have that this becomes sum 0 to infinity of cn n minus 1 x to the n minus 2, nothing to move in there, plus sum n equals 0 to infinity of 2 cn n x to the n, all right, and then minus sum n equals 0 to infinity of 3 Cn x to the n plus 2. All right. Now, what comes next? Well, the next thing is we need to shift. We need to shift so that all our exponents look the same. So here, this we're pretty happy at. So we'll just say L equals n. Now, how about here? Well, we want everything to look like x to the L. So here we'll say L equals n plus 2, or of course we could say n equals L minus 2. And now on this part here, well, again, since our goal is to make everything like x to the L, L equals n minus 2, or n equals L plus 2. Okay, so we're still the same problem. We're just rewriting it in a different way. So this becomes what? Well, the sum L. Now, let's think about this one here. Originally, it starts at 0, and then you're like, oh, now it's going to start at negative 2. But let's talk about this sum. Where does it really start? When I plug in 0, I'm going to get 0. When we plug in 1, we are going to get 1. So we can say, hey, you know what? Let's just start this at 2. All right, let's start at 2. So now, this n minus 2, because I start at 2, starts at L equals 0. Nice. Okay, then we have C, L plus 2, and then we have our L plus 2, L plus 1, and that's x to the L. All right, so that's our first thing. First sum. The second sum, we actually don't even have to really do anything. The only thing that happens is that wherever we see an n, we put an L. Okay, great. Our last sum. Well, here things get a little bit interesting. And why? Well, because we're going to start it at 0. So when we do n equals 0, 0 plus 2 means here we start at 2. So 2 to infinity, and then we have 3 C L minus 2, and then we have x to the L. All right, good. So we're ready to put all these together, except not quite yet. What's wrong? What's wrong is we have to make the starts line up. They don't line up yet. But that's okay. We can do this. We can do this. We have the technology. I'm anticipating I might need more paper. That's all right. Plenty of paper in the world. What we can do is we pull terms off. So if we pull terms off, we'd pull off the L equals 0 term, and that would give us C2 times 2 times 1 times x to 0, which is 1. So 2C2. All right, so that's our constant, if you like. Now here, when we plug in L equals 0, we get 2C0 times 0, which tells us that that's 0. Okay, so in fact, that's our only constant term. That's great. Plus, now we go to our next piece. Okay, our next piece would be plug in L equals 1. So we'd have C3 times 3 times 2. So that would be 6C3. That's L equals 1. Here, plugging L equals 1, we're going to get 2C1 times 1. So 6C3, I can say the words, plus 2C1, and that's our coefficient for x. And now we've taken care of 0, we've taken care of 1, and then we say everything else goes into the sum, plus the sum from 2 to infinity, and now we group things together. So we have well, CL plus 2 times L plus 2, L plus 1. And that's from the first part, plus 2CL times L in the second part, minus 3CL minus 2 x to the L. All right. Whew. Good. Now, we're almost done, and unfortunately, we just need a little bit more space than what we have on this piece of paper. So we will go to a second piece of paper, but just barely. Just barely. Okay, so what do we need space for? Well, this part right here is our recurrence relationship. And so, remember, because everything equals 0. So we actually can say each one of these pieces equals 0. So we know that 2C2 equals 0. We're going to come back to that in a second. 6C3 plus 2C1 equals 0. We'll come back to that one in a second. And here, we'll get that CL plus 2 times L plus 2, L plus 1, plus 2CL times L minus 3, CL minus 2 equals 0. All right, each one of those equals 0. All right, so let's pull this back down, and we'll pull this up here. Now, when it talks about the recurrence relation, that's going to come from this piece right here. And so in particular, if you solve for CL plus 2, so C times L plus 2, and I should have put a note here. This is for L at least 2. So CL plus 2, you move those across. So that would be 3 CL minus 2 minus 2 CL times L, all divided by L plus 2 times L plus 1. All right, so that's our recurrence. So this is a piece of our answer. Good. Now, how do we get the rest of it? Well, what's the rest of it? We need to find the first 5 terms. Now, we have some nice pieces of information. Y of 0, well, we can actually see what happens. If you plug in 0, the only thing that doesn't vanish is when x to the 0. So this part right here is really C0. Y prime is 0, by a similar thought process, you take the derivative and then you plug in 0, and you see that what you end up with is that you end up with C1. So we have C0 and we have C1. Now, let me just add a little tiny note of caution. If we had a third initial condition, so we had a triple derivative, y double prime of 0 is not C2, right? Because be careful, because powers come down. So that's just a little side note. Who knows if that'll ever show up in the future? It doesn't show up today. All right, so the good news is we know C0, so C0 is equal to 4, C1 is equal to 3. Do we know C2? We do. 2 times C2 better equals 0, so what is C2? C2 is 0. All right, well, that's great news for us. How about C3? Come to the next one. We say, oh, well, 6 times C3 plus 2 times C1, well, C1 is 3, so plus 6 has to equal 0. So what is C3 to make that true? So that says C3 is minus 1. Now, what about C4? Because we have to go up to C4. Then we use the recurrence. So C4 is, what are we using for L? That would be L equals 2. So according to this, it'd be 3 C0 minus 2 C2 times 2. So I'm just putting, everywhere I see an L, I'm putting in 2. So 2 minus 2 is 0, 2, 2. Downstairs, 2 plus 2 is 4. 2 plus 1 is 3. Well, what do we know? We know C0. It's 4. Okay, so that's 3 times 4. C2 is 0. Minus 0 over 4 times 3, which gives us 1. All right, so if we put it all together, we can say, all right, well, our series solution starts as 4 plus 3x plus 0x squared minus x cubed and plus x to the fourth. And that's all we need. Of course, there's a dot, 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 but we don't need to know what's going on with the dot, dot, dot. The dot, 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 we would use this recurrence relation to keep going. And there we go. Wow, the end. What? That came too soon. Can't we do one more? Just one more, like a bonus problem? Ah, okay, you talked me into it. You talked me into it. Bonus! Let's do it! All right, a special one. Okay, find the function f of t which satisfies f of t minus 1 is equal to the integral from 0 to t e to the minus tau f of t minus tau d tau. And it says, hint, take the Laplace transform of both sides. So, like, okay, cool. So we'll take the Laplace transform of both sides because that's what the hint tells us to do. The hint wouldn't lie, would it? Well, I hope not. Okay, so let's do this one. Now, if I take the Laplace transform, well, the Laplace transform of f of t minus the Laplace transform of 1 is equal to the Laplace transform of the integral from 0 to t e to the minus tau f of t minus tau d tau. But we might say, wait a second. That looks familiar. We talked about it a little while ago. That's convolution. So this is really the Laplace transform of the function e to the minus t convoluted with f of t, which, by principles of Laplace transform, that's the Laplace transform of e to the minus t times the Laplace transform of f of t. Okay, all right. So what do these pieces become? Well, the Laplace transform of f of t, we'll write that as capital F. Laplace transform of 1, that one we should hopefully know. That's 1 over s. Laplace transform of e to the minus t, 1 over s plus 1. And the Laplace transform of f of t is, again, f. So there we go. Now we're like, wow, that doesn't seem so bad. Well, we move stuff around. So f, I'll move this subtracted. So 1 subtract 1 over s plus 1 is equal to 1 over s. Okay, all right. Well, Now, this becomes, well, we'll do it in slow motion, s plus 1 over s plus 1, subtract 1 over s plus 1 equals 1 over s, or f, s plus 1 subtract 1 is s over s plus 1 equals 1 over s. All right, we're going pretty good here. So f, the Laplace transform what we're after, we flip this over as we bring it across. We get s plus 1 over s times s is s squared. Or that says the Laplace transform what we're after, s over s squared, 1 over s plus 1 over s squared. Now, that tells us, hey, once we took the Laplace transform, we got into an algebra problem, we've solved the algebra problem, now do the inverse Laplace transform, and what do we get? Well, inverse Laplace transform is our f of t. Inverse Laplace transform of 1 over s is 1. inverse Laplace transform of 1 over s squared? Well, do you know it? Hopefully it's somewhere here. It shows up 1 over s squared. It comes from plugging in n equals 1 into there. So it's actually t. And we're done. Our function is 1 plus t. Wow. That's kind of cool. You know, when you look at this problem, it looks intimidating. And it's like, what? Can we do it? Do we have the tools? But then we just say, well, let's just do it and let's see where we end up. And we end up with a really amazingly clean answer. Like, that's a very simple function. And we didn't need to use anything fancy, just using the tools that we had. Now, you might be wondering, could we have done this in a different way? Okay, let's do it. A bonus, double bonus round. Okay, so here we go. We're going to do it without Laplace transform. But we're still going to use differential equations, which means that we're only going to use the tools that we've learned in our class. Now, the first part is a little bit subtle, but it comes back to something we've mentioned before. And so recall, and we're not going to go through it, but namely, when we talk about convolution, it doesn't matter which order we do the convolution. So f star g is g star f, which really comes down to a simple substitution. So if you put in u equals t minus tau and work out what the substitution becomes, that's the result. Okay, so here we go. F of t minus 1 is the integral 0 to t. And now I'm going to pull in this card. So instead of having f of t minus tau, I'm going to have e to the minus t minus tau. And then I'm going to have f of tau d tau. All right. Same problem, right? All I've done is I've changed the order of convolution, which doesn't change anything. But the fun parts begin. This will be the same as, well, integral 0 to t of e to the minus t, e to the tau, f of tau, d tau. Now, question for you. When you look at this part right here, this part being the e to the minus t, with respect to this integral, what is it? Now, the integral is with respect to tau. E to the minus t has nothing to do with tau. It is a constant. And what can you do with constants? You can pull them out. So we can pull that e to the minus t out. All right, great. So we get e to the minus t, integral 0 to t, of e to the tau, f of tau, d tau. And now you're like, what have we accomplished? Well, we're getting close to something here. I'm going to move that e to the minus t to the other side. And what I'm trying to do is I'm trying to isolate that integral so that the only place where t shows up is right there. See, currently, when we started, t showed up on the inside of the integral. I'm trying to pull it out. That's what we were able to succeed. We were able to pull the part with t completely out of the integral. And now I'm going to pull it all the way to the other side. So that, which means multiply both sides by e to the t. So that we have e to the t times f of t minus 1 is equal to the integral 0 to t of e to the tau, f of tau, d tau. Multiply both sides by e to the t. And now, what can we do? Can you see it? It's something a little fun. It's a fundamental theorem of calculus. Yes! Here we go. We're playing the big card, the fundamental theorem of calculus card. Take the derivative of both sides. Now, on the left-hand side, work is involved. Product rule. So, derivative of the first, e to the t, times the second, f of t minus 1, plus the first, e to the t, times the derivative of the second, that's our f prime of t. And the minus 1 The derivative of that goes away. So the derivative of the left equals the derivative on the right. And the fundamental theorem of calculus says if I take the derivative of an integral, I get the function e to the t f of t. Okay, so, or you get e to the t f of t, that's this part, minus e to the t plus e to the t f prime of t is equal to e to the t f of t. And some nice things happen. The e to the t f of t is canceled. We can divide out by e to the t because e to the t is never 0. And we come to the conclusion that f prime of t has to equal 1. So, we're doing great. Now, see, that's a differential equation. A really good differential equation, the one we can solve. But how do we actually solve it? Well, this one we can do from Calc 1 tools. So, we say, aha, f of t is equal to t plus c, where c is a constant. Now, at this point, you're like, aha, ha, 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 we're stuck, because we don't know what the constant should be, but we can figure it out. So, let's do a little note. So, our note, at t equals 0, what do we have? We have that f of 0 minus 1, I'm working with the original equation, is equal to the integral 0 to 0 of the stuff d tau. But what happens when you integrate 0 to 0? You get 0. So that tells us that f of 0 needs to equal 1. So now, since we know f of 0 equals 1, we can keep going. We say, well, we know f of t equals t plus c. So f of 0 equals 0 plus c equals 1. So that tells us that c equals 1. And so we end up with our final answer, f of t is equal to t plus 1. And there we go. No Laplace transforms involved, but I will say between the two, I think Laplace transforms was a little bit more slick and probably a little bit more intuitive, because there was sort of like, oh, f star g is g star f, move things around, which is not the first kinds of things we think about on these kinds of problems. But it's kind of cool that, hey, we could do it in these two different ways, and the answers were the same. That's a good sign. We're getting to that part where it's like, wow, we have multiple avenues to solve problems. And that means it's more fun, because we get to explore, and we get to pick the ways that we like to do it. So anyways, well, that's the end. We've reached the end. Thanks for coming along. I hope you've enjoyed everything, and maybe someday we'll get to meet again. All right. Bye.